Okay, number 15. All right, I'm going to need some room to solve this. So I'm going to erase the given. Basically, the given tells us we got the length of the string. Oh, and then this theta right here is 5 degrees. What else is in there? And then the charges are identical. So they're either both positive or both negative. It doesn't matter as long as they're identical. Let's just say that they're both positive. Okay, so we're going to make some room and solve this. So this problem begins with a free body diagram. You know, it's a force problem. Force problems are, you know, the way you approach them is you go free body diagram, sum the forces, and then figure it out from the summing of the forces. So you can focus on either sphere. They're identical, right? Everything's identical. The left side and the right side are the same. So why don't we focus on this guy right here? So if we do a free body diagram for that sphere, okay, so what are the forces on that sphere? We got mg down. We have tension up like this. So if this is 5 degrees off the vertical, I like angles off the horizontal. So what would this be? That'd be 85, right? If that's 5 degrees, then this is going to be, this angle in here would be 85. Okay? And then the one additional force, it's an electrostatic force, right? Because charges exert forces on each other. We have positive charge, they're going to repel, which is why the spheres are swinging out like that. Okay? So this is going to be an electrostatic force. And then what's the equation for the force between charges? K Q1 Q2 over R squared. But what do we know about those Q's? They're the same. So Q1 times Q2, let's just simplify that to what? Q squared, right? Q times Q would be Q squared, and they're the same. Okay, we're going to need R. Now, what's R? It's the distance from sphere, from charge to charge. So how do we get this R? Well, we got to do some trig. So here's a triangle. Can we solve for this distance right here? Yes. What's that distance going to be? Sine of 5 times 30 centimeters. But we want to, what do we want to do to the 30 centimeter? Centimeters needs to go to what? Meters. 0.3 meters. So that's sine of 5 times 0.3. So that gives us 0.026147 meters. And then we double it, right? Double it for this whole distance. Okay? So the R is going to be 0.052293. That's the total distance from there to there. Just trig. Easy enough? Okay. So now what do we do? So here's our free body diagram. What do we do after the free body diagram? Sum the forces. Let's shrink this down. Make more room. Okay, so here's what your summing of the forces should look like. You sum the forces. In the x direction, we have k q squared over r squared. That's the force of the that's the electrostatic force, minus cosine 85t. Okay, those are the 2x forces. Sum of the forces always equals ma, or that would be an x acceleration. But is it accelerating? Is this sphere accelerating in the x direction? Or just sitting there? Just sitting there. There's no acceleration, right? So we can just set this to 0. Okay, so that's our x equation. So now we do a y equation. In the y direction, we have two forces. We have the y component of tension, which is going to be sine 85t minus mg, right? And those are the only two forces in the vertical. sum of the forces equals ma, but is this charge accelerating in the vertical? No. So we can set that equal to 0. There's no acceleration. Okay, the rest of the problem is algebra. Make sure you put this 0.2 kilograms. What do you got to do to the mass? So they give us a mass of 0.2 grams, 0.2 grams. What do we have to do to that? Put it in kilograms. So that's going to be 2 times 10 to the negative 4th kilograms. Now look, why do you have to be in kilograms? Let me just tell you. Because look, what is K? K is 9 times 10 to the 9th Newton meter squared over Newton meter squared over Coulomb squared. Look at, what is a Newton? A Newton is a what? Kilogram, oops, I'm messing up today. Kilogram meter per second squared. So you've got to be in kilograms because that's what the constant uses, right? Notice, what else is the constant using? Meters, which is why we had to convert centimeters into meter. All right, so solve for t. You can take this equation. Look, we got m. M is 2 times 10 to the negative 4th. G is 9.8. When you solve this for t, you should get, and don't round this, 0.00196,749. That's good enough. Just, you don't want to round it because you'll get rounding error. So then take that tension, take this, plug it in up there, and now you can solve for Q, which is what the question wants. Okay, so take this equation, plug in T, we got R, here's your R right here, plug that in there. K is 9 times 10 to the 9th, Newton meter squared over Coulomb squared. When you do the algebra, I'm going to leave the algebra out. You guys don't need to watch me do algebra. Solve the algebra. The answer comes out as 7.2 times 10 to the negative 9 coulombs. Now what's 10 to the negative 9? Nano. So the book, the answer in the back of the book, they say 7.2 nanocoulombs. Nano is times 10 to the negative 9.